So we can start. Welcome to MGM course. So I would like to discuss two things today. I will go through the assignment problem as well in case you have doubts, and then we will discuss divergence measures. So divergence measures play a key role in designing generative models. So you will see this again and again. So maybe many of you may have already seen something called KL divergence, but there are many others. But essentially, KL divergence plays a very big role, but we will see a few others. Okay. So the reason why assignment problem we will discuss is that it will be related to the quiz as well, and there is less time. So the quiz will be based on some of these problems. So first problem, if you recall, in the assignment was very similar to what we did in the class. It's a MLE estimate. And similar problem, bag with two balls, green and blue, and you took 6 samples from the bag, and then you have this output, these samples. So you can encode one of them as 1 and other one as 0, just like we did in the previous class. And then you have to fit a parametric distribution. So you know very well which type of parametric distribution will be good for this when you have just 2 outcomes. So that's basically, this is the same very similar problem. Okay. So the only thing now you have to do is that by hand you can learn this distribution, because you will solve this optimization problem and so on. So you do this by hand, and once you know the distribution, how you sample the distribution is from the distribution is something where you need a Python. Okay. So you will use this binomial, random.binomial, and it's there in the NumPy. So you can call this with, but this is binomial, right? So Bernoulli is just 1. When n is 1, Bernoulli is you can get Bernoulli from the binomial, right? So you can put n equals to 1, and that behaves like Bernoulli, and p is the parameter that you learn, right? So all this distribution fitting that you did, the theta that you saw, that corresponds to that p here. Okay. So the way you wrote parameter there was theta over 3 or something like that, right? So there you have to kind of use that here. Okay. So you may learn about NumPy from the doc here. This is very easy to learn. Okay. So about very basic about NumPy, you can go and check this doc here. As I said, you can use Bernoulli for binomial n equals to 1, and as a maths problem, you can think of proving this result, that binomial PDF can be obtained via an independent Bernoulli. Okay, so that's something you may try by yourself. This is indeed true. If you multiply an independent Bernoulli, you get the PDF of binomial. Okay, so that's easy to prove. And if we look into problem number 2 is on inverse CDF approach, and this is something we did in class as well. One example we did. So generative modeling problem is a problem where you are learning a map G that takes you from a known distribution where you can sample easily, in this case is Z, and then it gives you a generated sample. So G of Z will be some generated sample. Okay, that comes from X. Okay, so this usually involves 2 steps: sample from known distribution. So in the inverse CDF approach, what we saw is that Z in our case is the y-axis, which happens to be the range of the CDF. And range of the CDF is between 0 and 1. We all know probability values cannot go beyond 1, and it starts from 0, cannot go negative also. Okay, so this is guaranteed that we have CDF values can only go between 0 and 1. And in the inverse CDF approach, our G is F inverse basically. So we look for an entry in the y-axis, and we see what is the inverse of that via F. And then that gives us the entry from the x-axis, which is our sample. Okay, we have discussed this in class as well, that it may not be invertible. Then in that case, F inverse stands for the inverse map. Okay, so the inverse map will be a set in that case. When we talk about invertibility, then inverse is a function when you have one input, you have unique output as well. But if it's not invertible, then it's possible that for one input f inverse will give me multiple output, which is possible. As we have said, we can encode it like this, that f inverse y, it's possible that f inverse y is not a one entry, but in our case it's samples, so it could give you a set of samples which is in A. Okay, and what will you do in that case? Because you have multiple, then the one way is just pick one of the entries of A uniformly, sample as you like, and report that as generated sample. Okay, so problem 2 continues. So now in the assignment I go ahead and kind of give you more precise problem. So it's about rolling a 6-sided die 10 times. So basically this means that you will get 10 samples after rolling a die, and since it's a die, then the numbers you will get will range from 1 to 6. And in this case, in the first roll die roll I got 1, second one I got the number 3 on the die, and so on. So these are my samples. Now you can compute the PMF values for the possible outcomes of a die is 1, 2, 3, 4, 5, 6, and now PMF value will correspond to the probability of one happening based on the sample that I got. So for example, what was the PMF of 1, or the frequency of 1? So in this case it was only once it was found. So basically 1 over 10 in this case, right? And then if you see 2, then 2 occurred 1, 2, and 3 times, right? So 3 over 10. So that's your PMF value. So these are the PMF values you have to plot. On x-axis you only have the possible outcomes. Okay, so these are unique in this case. So on x-axis you will have 1, 2, 3, 4, 5, 6, and y-axis these are the probability values computed from the samples. So then you get the PMF values and you can plot that. But what we really need are the CDF values, but CDF values we get after doing the PMF, because CDF is cumulative of the PMF probability values. And there are some typical questions. Is the CDF graph that you got is strictly increasing? So what do you suggest in this case by looking at this outcome? Is this CDF graph going to be strictly increasing in this case? So how is the CDF? Because it's discrete value, we have to be careful, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So at 1, right, what is the value at 1? 1 is 1 over 10, right? So let us say 1 over 10. So let us say the maximum we so 1 over, so we get 1. So let us do 10 divisions, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1 over 10, and then 2 is 3 over 10. So 2 is 3 over 10. So this is 3 over 10. Okay, and 3 is how much? 1, 2, 3, 3 over 10, right? So again it's 3 over 10, right? And 4 is 1 over 10, and 5 is 1 over 10, 6 is again 1 over 10. Okay, so these are the PMF values. Just because of one value it did not become uniform, so it's not exactly uniform. So now if we have to plot the CDF in the same place, we can plot the CDF, right? So CDF is cumulative up to 1. Okay, so cumulative up to 1. What is the graph like this? Okay, and then it is cumulative up to 2, right? So what is the graph for cumulative up to 2? Okay, so until 2, what are we going to get? Or strictly less than 2, what I am going to get? So should I add the 2 values? Another value that I got at 2, between 0 and 1 it will be 0. 1 and 2 is 1 over 10. It should not exceed 1. That's what. So we have to be sure. Okay. So with 0 and 1 it's 0, strictly less than. 1 and 2 it's 1 over 10, and between 2 and 3 it's 1 over 10 plus 4 over 10, and then you are looking here from 3 to 4, 4 over 10 plus 7 over 10. So 4 over 10 plus 3 over 10 I mean, so which is 7 over 10. So 7 over 10 is here, okay. So 7 over 10. Usually we do this to mean that this value is not, I mean it does not go exactly at 3, there is a jump. So this value is attained here, at 3 there is a jump. So basically we do this, and at the last step there will be 1, right, because it accumulates to this. So in the discrete case we have to be sure that when CDF is, CDF is not necessarily invertible. Actually it will not be invertible in the CDF, because it's always like staircase and there is a flatness. So for example, exactly at if I see at 4, there are many values for which it's 4, okay. So it is certainly not, because it's a stepwise function. CDF is stepwise function. It is increasing but not monotonically increasing, not strictly increasing each time, but it is increasing, okay. The next values are greater than or equal to the previous values, but not exactly greater. So this is the case, okay. So in the discrete case, let us make it clear that it is certainly not invertible. Continuous case we can see later, okay. Then the inverse CDF method says that you pick some samples in 0, 1, because this is indeed guaranteed to be 0, 1. So pick any sample, because this is a 0, 1 interval, and you can use uniform sampling. It is still producing some randomness, which is what we want for generative model. There should be randomness obviously for generative model, otherwise it will produce the same, it will memorize and things like that. So here the variations that you see here will create variations in which of the CDF it is going to pick, okay. So once it's going to pick one of the CDF, then we will get to the so it is possible, because it's 0, 1, we are not supposed to use the values that directly correspond to it. It could be some value in between, but then we have to check from here whether it's closer to this guy or this guy, okay. That we can do it by checking the, so this guy, if I somehow choose this entry, then I will check the difference. This minus this is smaller than this minus this, or this minus this. So since this is smaller, I will generate 3 sample 3, because it's closer to 3, because our sample are discrete. So we have to put this in any one of these 1, 2, 3, 4, 5, 6, okay. So if it is closer to this, then we will say it's 4. If it is exactly in between, then again you can do a coin toss to pick any one of these. It can happen that it is exactly in between. Then again you do some coin toss, you do Bernoulli. It can be done in the code, generate something from the Bernoulli, and it will tell you heads or tail. So this guy will be head, this guy will be tail. So you decide which one to take. So this is the inverse CDF method, and what this assignment does is makes things a little bit more precise for you to even code in Python. So this was an example that we can do on paper, and you can generate some samples like that, and then we can generalize this by writing some Python code, which is also pretty straightforward, I would say. It's just that when you are generating the samples, make sure that the samples are usually more than the possible outcomes, okay. So in this case, the possible outcomes that I choose is n, that n correspond to 6 here. So it's like you have a n sided die, okay, and usually you will keep number of samples which are, let's say, order of 2n, okay. Then you may use the Python inbuilt library, and you can go there and do n numpy the histogram, and let it plot the PMF values for you, and and A will be the bins are n, and I guess A is the input vector. Yeah. So basically, you will sample first. You will call the library to Python library to sample these k equals to 2n entries, and since these guys are independent, you may use Bernoulli for each of these 2n to sample. So basically, you call Bernoulli 2n times, because throwing of the die and all this, they are not dependent, which 1, 2, 3 are not really. So basically, I will do 2n Bernoulli calls, and so this could be done just like in the previous case. Okay, so then we have k samples, and this k samples goes here, and you can use this to plot PMF values, and bins are telling you the possible outcomes. In our case here, bin was 6, so here it's n, and then it should plot it should help you in plotting the histogram PMF values from there, and then you next step would be CDF values. So how to now first entry, and the CDF will be first entry plus the second entry, first entry plus second plus third entry. So basically, you may also use the inbuilt I mean some examples on how to compute the cumulative PDF. So once we have the cumulative PDF in the Python code, then more or less you are done, because your possible outcomes were this array, which you generated via 2n binomial calls. So you have this generated samples, and you have, so these are your possible outcomes. So x1, x2, x3, xn, and the cumulative will also be discrete values, which is f1, f2, fn. Okay, so basically now you have x1, x2, xn, and you have the cumulative values f1, f2, fn, and they take values between 0 and 1. Okay, so we have the array and vector, we have the f values calculated for those, and that is what we need now to generate via to generate via inverse CDF method. Basically, we have to now sample u on the y-axis, basically. So pick any u between 0 and 1 uniformly. Again, you may want to use Python library for random sampling. So that's what I'm saying here. U from uniform distribution. So you can use numpy.random.uniform to pick one random sample, and once it does that, as I discussed some time ago, now you have to find where this sample is between u minus fi xi and fi plus 1 xi plus 1 minus u, right? So these are f of x2, right? So f2 depends on x2, f1 depends on x1. So in general, I have written fi takes xi argument, fi plus 1 takes xi plus 1 argument, and I am checking where is the u closest to, whether u was closest to the CDF values fi, or whether u was closer to the CDF, because, and I have reversed this sign, because this is necessarily greater than this, and this is necessarily greater than this. Once I know where it goes in the bin, which of these it goes, and then I'm looking at argmin. So basically, argmin says for which of the xi's, right? So in this case, there are only two options. So basically, this means for which of the xi or xi plus 1 the minimum is achieved. Okay, so that's exactly the same thing that we discussed. You will correspond to left one or right one, right? Sample. And doing that for whichever of xi or xi plus 1 the minimum achieved, we will generate that sample. Okay, and if there is a match, in case it is exactly in between, meaning u minus fi xi and fi xi minus plus 1 minus u are the same, in that case pick any one of the report any one of here again slight correction, rather than saying fi or fi plus 1, I should say xi or xi plus, because xi or xi plus 1 is our sample. Okay, so then it's like you are in a tie of producing xi as a sample or xi plus 1 as a sample, but you can again decide with a fair coin toss which one to report. Okay, so this is the second assignment, which is the inverse PDF method. All these ideas will be expanded, generalized. Okay, that's why it's good to start with a good concept in the beginning. Okay, the third problem is also related to the initial intuition that we developed. Okay, this problem again is similar to what we did. It uses chain rule. So I just gave it a little bit of a twist. So chimpanzees and humans differ when you look at the genetic pattern. They are 99 point something. They are very, very close. Okay, so it's a, if I understand correctly, this is still a mystery. What exactly, like how do you explain the differences? They know by looking at the DNA sequence. They know that there are certain differences, but maybe they don't know the exact algorithm to define these. Okay, so there are very few differences in the genetic code of chimpanzee and humans. So it is a string problem. Okay, so DNA, we can see this as a string. A, T, G, C, these are the sequences usually we see, and how they differ defines how we differ between each other and also other species, right? So so we will simplify a little bit. So we want to create a human-like genes. We want to generate. Okay, so we want to create genes by ourselves, and let us assume that for simplicity, there are two out of A, T, G, C. There are like two which are prominent, that decides the differences between them. So let us say we denote them by 1 and 0. Let us say it's A and G, and we denote A by 1 and 0, and their occurrences or co-occurrences in a certain way decide, let's say, what could be human and what could be a chimpanzee. Okay, so what we will do, because since we want to learn the genetic modeling part, we want to generate these sequences, right? So what we will do is that we need a training data, obviously. So we have reference of many people. We will take some samples or DNA samples of all of them, and because we are interested in generating human, we will not mix with chimpanzee. Okay, because in genetic modeling, unless you do any contrastive learning or something like that, in genetic modeling you want to use the samples only in the training. We only want to use the positive results and want to generate positive results. Okay, so let us keep things simple for the moment. Okay, so so we will take a random samples, as we have seen these samples, and let us say they are of length 10 only, but in general in reality they are very big, millions I guess, and let us say we take only 12 samples. So this is your data. You went out, you collected the gene of 12 people, and this is the sequence you got. Okay, so this is the sequence you got. Now one of the common string, I mean, when we got the data, in this case we can say that okay, I can find some pattern, but in general you will not, because if you specifically find the pattern just by observing, then maybe you don't need the genetic modeling. Okay, you may hand code things, and that's what you need, right? Some pattern you know for sure that it's responsible, and then you will just write a deterministic algorithm. But so in this case, like in general we will not know, but let us look at the data, and because I created the data with a I created the data in such a way that there will be some pattern. Okay, so the two patterns that I created was 101 and 11 string is there in the data. Okay, in all the samples. Okay, so I believe, I hope I have not done mistake. So 101 is there and 11 is there. 101 is there and 11 is there also, although they are not separate. Okay, so all this 1 is there, but 101 is also somehow there. 101 is there, 11 is there, 101 11 101 11 01 11. Okay, I don't even know if that makes sense. In fact, I rely on your outcomes, the codes that you will write. Then I will analyze from there what went wrong or whether this model was good or not. In fact, I have given you many steps. If you go through the steps, it should capture the essential things. So okay, so perhaps we feel that 10111 sequence decides these genes. Okay, so this DNA sequence. Okay, so our goal is to generate similar ones. Of course, during generative process, some may come out to be defective. So as the nature of this generative model is, there is a likelihood, okay, because at the end of the day we are only dealing with probability. Nature doesn't ensure everything for sure. This is why you see birth defects and things like that. Nothing is, there is some possibility, okay, rare cases, hopefully very rare cases, okay, but we do see disabilities due to defective genes or things like that. Okay, so at the end of the day, nature is also doing generative process, but is trying to minimize that as far as possible. But there is no guarantee. There is no zero probability that no one will be born with disability. Okay, so things may go wrong. That's what I'm saying here. When you generate these samples, when you train your data, you generate these samples, there is possibility that what we were looking for is never produced. Perhaps that corresponds to defective genes and so on. Okay. So how we will model this problem? Okay. So we are given samples, 12 samples. We have some ones and zeros there, and our goal is to generate data that corresponds to this distribution. Okay, or you can see this as a 1D image, right? With 1 corresponds to black, 0 corresponds to white. So the fact that 101 is there, perhaps it means that the object that looks like 101 is what we are trying to learn. Okay, or combination of 101 and 11. Maybe it resembles something, okay, in real life maybe. We could have made this into 2D also, okay, but for simplicity let us focus on 1D case. Okay, so this is the problem. You have to build a generative model that creates this kind of data. Now the first step, as usual, is how we will do the modeling, right? The maths modeling, not the other modeling. Okay, so how should we go about that, right? So this is a problem, right? And where are the random variables, right? So and these are now tuples, right? So these are tuples 10, right? 10 tuples, right? And each of them are random. Okay, so it's like each entry could be modeled via a random variable. Okay, each entry modeled via a random variable, and there are 10 random variables in our problem. Okay. Okay, so this is the setup, and in this example, I of course maximum likelihood is there, but if you assume the complete independence, it will not work, right? The joint probability is equal to product of the individual probability will not work here, because this is a problem where there are dependence involved. It is not completely like I am throwing 10 coins independently. So the modeling assumption that I will model this as product of individual Bernoulli will not work, because this is like there is a pattern somewhere, okay, that needs to be captured, and this pattern is also kind of shift invariant. Okay, so it's also not like Bernoulli with different parameters. You may say that, but it's like a, because once I see 1 and 0, the probability of 1 happening seems to be high. Okay, because this guy is present in almost all the samples. Okay, this is what we want to capture, occurrences of certain pixels ensures the occurrence of other pixels. So this could be extended in a very high dimensional case like color images, cats, and so on. Occurrences of certain pixels in certain way gives you more likelihood of certain other pixels that can make it a cat, right? So now we go back to the maths. We have seen in the previous class that according to that we have 10 random variables, and we are trying to figure out what is a good way this random variable should occur, okay, such that it matches the samples that I have seen. Okay, the occurrence or co-occurrences of these matches the samples. So in this case, we have seen in the last class that one possibility is chain rule, because complete independence doesn't work. As I said, it's a wrong assumption to assume n independent coin are being tossed, so that goes out of picture. So here we have chain rule. We have seen in previous class, even in chain rule, we could have used all previous dependencies, right? That is like the perfect case. That is the actual chain rule. So this is not necessarily equal. Actually, it is approximate. Okay, so this should be approximate, because in actual chain rule would mean that now there is a Markovian. We assume Markovian, meaning that my next pixel only depends on the previous pixel, right? So we have discussed this in the last class. So if that is the assumption, then I plus 1 pixel depends only on the I, not on I minus 1 and so on. Okay, but in the exact chain rule, actually ith pixel should depend on all previous one, may depend on all previous one. So to ignore and say that it only depends on the previous one can be a problematic assumption. In fact, it could be. It could be. Okay, it depends if you're lucky, and this is something I want to figure out with you also, with the coding. Okay, so there are two strings, right? 1 1 and 1 0 1. So I have put both there for some reason. If you go with Markovian property, then I'm expecting that the pairwise it should cover. Okay, this 1 1 pattern it should be able to generate. Okay, because it is a 2-length string. But if it's 3-length string, and if it only looks at just the previous one, having seen 1, it can produce 0 because it has seen 1 0 many times, let's say. Okay, but by then it might forget, because if it is at 0 now and it is looking to produce 1, so having seen 0, it has to produce 1, right? But it has forgot about the previous one, perhaps because of the Markov property. If it was exact chain rule, then it will remember this and this. You say, okay, having produced the current one and also having produced the previous one, what is the likelihood of producing 1? Because such strings are so many there in the sample, it will be forced to learn that way, because we are doing the maximum likelihood estimate anyway of this. So we will force that these are so many, so you should and since there are so many samples there, the likelihood of these sequences occurring should be maximized. So I don't know for sure right now what will be the outcome of your code. I want to see from your experiments, but I want to see. I will be interested to see. As I said, I just made this. I cooked up this assignment. And even I don't know what this model will do. So do this. We will be looking at this with excitement, whether this learns this or not. Okay, there are a few more details, like how will you go with this, right? So far you know that. So far what you know that this is the model, but then many of you would be thinking, but how to parameterize this, right? What we know so far is the first one, because this is like the back problem, and this only depends on the first string of the sample. So this is if I basically you forget all the string, then essentially I am looking only at the first bit of each sample. So this is like just focusing on the first bit. So there are and there are 2 balls in the bag and I pulled 12 times. This is exactly the same problem. So P theta 1 x1 is exactly the bag problem. Okay, so you can learn this exactly like you did it for the bag problem. Now what happens for theta 2 x2 given x1? Now there is a conditional, right? So how do you learn distributions like this? Now x1 is binary, so it could get 1 or it could get 0. So now you have a branching going on, right? So now your distribution will be depending on x1 being 1 or x1 being 0. If x1 is 1, this is a different probability distribution you are going to learn. This is P theta 2, I will call it 1. So this is different. Theta 2 combines 2 parameters now. Theta 2 1, I will call it theta 2 1, and it came via the left branch because I call left branch as x1 is 1. So then it goes, so x1 is 1 and then I'm learning x2. So x2 given 1. And the other branch is P theta 2 x2 given 0. I mean this is 2. You get that? Now there is a choice to be made. This is like a choice tree. So that's why we call in the last class that this needs a 2 parameter model. To having known x1 is 1, still I have to learn, because for x1 equal to 1 there are many samples there, and I'm supposed to look at this now. Having found x1 is 1, okay, so x1 is 1 is your first bit, right? So which are those cases you will focus now? 1, S1, S3, S6, S7, S10. Your sample reduces. That's what conditional probability does, right? Having seen something, your original sample reduced, because now you have to focus only on the sample which is conditioned on. So x1 is 1, you will focus on these samples whose first bit is 1. And only now these are your defined samples now, and you can say new set of samples. You have to compute PMF values on the new reduced samples. Okay. So this guy, the left part, are the reduced samples where the first bit was 1, and since I am looking at x2, I will focus only on the second bit, obviously. So S1, S3, but that is because of the conditional. I focus on only the one which starts with first one, but then I will be working only with the second bit, because that corresponds to x2. The random variable 2 is for the second bit, right? So basically it is now still the bag problem. Okay, so it is still the bag problem, but what is the number of sample now? S1, S3, S6, S7, S10, 5. It is still the bag problem. 2 balls in the bag, 0, 1, 0, 1, 0, 1. You just pick those S1 which is 0, S3 which is 1, S6 which is 1, S10 which is 1. That's all. Okay, 5 you pick. It is still the bag problem. Okay, 2 balls in the bag, you have 5 samples, and you estimate the left branch via maximum likelihood. Okay, this is doable. And same thing you can do for the right branch. Right branch, you pick the samples whose first bit was 0. So S2, S4, S5, S8, S9, S11, S12. It may happen that it has more sample, but it's okay. And again, it's a back problem. Now your sample reduces to those with first bit is 0, and then you do the maximum likelihood estimate just like the back problem. Okay, you don't have to do all the conditional dependency and all is taken care of by the chain rule, but the reduced problem is still like a back problem. Okay, so that can be taken care of. So in the Python code, if you write, you have to keep these 2 values, left and right values. Okay, you may use tree like data structure if you prefer. This is kind of like a root, and so this is kind of like a root, and then you have the branches going on like this. Maybe, yeah, I guess. So but you have to store these 2 values for theta 2, and what you have to store eventually is just the parameter theta 2, which has two components for the left branch and the right branch. You store them, okay, and then you do this, and actually all other theta 3 also is a two parameter because of the Markov property. Theta 3 will also have two component only because it depends only on x2. So it will decide on x2 basically. So basically it will be x2, and then depending on the values of x2, whether it's 1 or 0, it will take left branch or right branch. So basically the calculations for 2, 3, 4 up to n is exactly similar. You can put this in a loop and save this left array, right array, okay, and for 2 to n you save these parameter values, okay. So now what will be the generative process? It is conditional, right, because generative process will be decided by the first one. The first one is like the back problem, but it is not necessarily fair problem, right? So it's not like, so the number of zeros is, I guess, more than the number of ones. 1, 2, 3, 4, 5, 6, 7. 7 out of 12 are 0. So there is a biasness towards 0, slightly bias, just one factor. So slight bias towards generating the first bit at 0 or compared to 1. Okay, so that's fine. So that will be decided by the P1. So when you do the sampling, you will go to Python and say with theta 1 that corresponds to my data, generate the first bit for me. Okay, so it generates the first bit depending on, there is a more biasness to a 0, so more often than not it will produce 0, and it will be Bernoulli. Okay, so you call Bernoulli with theta 1. Now depending on that, theta 1 being 0 or 1, you have known this. So if theta 1 basically if x1 is 1, then you use theta to 1 value, this parameter, left one. Okay, so this is decided by first bit decided by Bernoulli, fitted on the data. Second bit now depends on the first bit. So if first bit is 1, this theta 1 value and Bernoulli should be used. Okay, and if it is 0, then this theta 2 parameter for Bernoulli should be used. Okay, and this was only during, so you can forget about this and this. Now it's just like you just go to the Python and say since my previous first bit was 0, now generate a sample which I need in the second bit. Generate a sample with this theta 2 too. That's all. Bernoulli just needs theta 2 value. Just give that, and that produces a second bit. Okay, so there is this if else you have to do. Okay, now similarly you keep doing that because it's Markovian. The third one will only depend on x2. Now whatever you do, it will produce, because x2 is also binary, so it will produce 1 or 0. Now again, if it is 1, then you will pick theta 3 left branch, or you can call it theta 3 super 1, and then if it was 0, then you go for theta 3 2, which is the right branch. The same process repeats. Okay, same process repeats, and then you will generate all the n bits starting from 1 to n. Okay, so so this is what I wrote more or less in this. There is nothing new here. So you can read this again. If you have doubt, then you can ask me. Okay, so this is our first step where we focus on Markov property, where we only look at the first one. Of course, as you can guess, we could have extended this to more, maybe dependence on 2. Okay, so these are all same as what I said until now. So finally I am saying that you have generated all the t on to t10 samples and so on. So this is exactly the same, but what I want to see next is this guy. So assuming that those who have 101 and 11 strings are intelligent humans, how many out of 10 are found intelligent? So let us say you generated 10 samples. Did it capture 101 and 11? Okay, again these are my intuitions. there may be some intricate relationship, hidden one, that it is generating and which is relevant. Okay, I'm not sure right now. I will look at your code and see what does it generate or not, and so on. But this is something I'm expecting. And is it that 101 is not really produce enough because we use Markov property, and but however 11 it does produce, because Markov property is expected that it might capture 11. Okay, we expect, because it's just 2 string, so we expect that. We don't know for sure, but if it in case 101 indeed it fails to do that, then can we do two dependencies conditional on 2 variables, because we expect that having seen 2, the high likelihood of having 1 it should learn, because there are so many of these in the data. Okay, so the next extension is this. As I said, you can take 1 week of extension to do this. Here there is a little bit more. So if you see first one parameter model, second one 2 parameter model, just like we saw, but third one, how many parameter? How many parameter model we need? 3, or because you have to look at the conditions, right? How many possibilities are there for x1, x2? 4. x1, x2 has 4 possibility, right? x1 has 2 possibility, x2 has 2 possibility. It's like the combinations, right? 0, 1, 1, 0, 1, 1, okay, and so on. So 0, 0 also. So there are 4 possibilities. So basically at x3 now you have to maintain 4 parameters, okay, to predict the next branch. So as you can see, the complexity of the model is increasing. Okay, that's where we need maths, right? That's where we need maths. Like how much is good enough, right? So in this case, if we generalize to just 2, at having produced x1 and x2, now there are 4 branches. So x1, x2. Okay, so this is like 1, 0, 0, 1, 1, 1, and 0, 0. Each will have now 1 parameter. Okay, so this is our theta 3, I guess, theta 2, I guess, theta 1. Oh, there is a mistake here. It should be theta 3 here. Okay, theta 1, theta 2, theta 3. Now theta 3 will have 1 parameter, 2, 2, and 3, and 4. Sorry, why I'm writing theta 4, 3, 1. Theta 3, 1, theta 3, 1, theta 3, 2, and theta 3, 3, and 4. Each are Bernoulli. Okay, so from code point of view, now from third step onwards, since we fix at 2, third step onwards, each will have 4 parameters to keep in track. Okay, so this is a slightly complicated model, because 4 n minus 2, 4 of 4 times n minus 2 plus 2 plus 1. Okay, the first one needs 1 parameter, second one needs 2 parameter, and the remaining n minus 2 of them, starting from 2, needs 4 parameters each. So this is a slightly complicated model now. 4n minus 8 plus 2, 6 plus 7, right? So this is a slightly complicated model compared to previous one, when it was order 2n minus 2. Okay, the previous one. But it is. But if you implement this, it should be fun to see whether this improved in generating this kind of pattern. Okay, so do that as an assignment. Do that, and so is it becoming better at generating 101? Okay. So in general, from here should we conclude that if there is a string of length L to be identified, how many are good enough, right? Should we go for conditionals with previous L minus 1, or L, or like what do you suggest, right? I'm just asking for intuition here. In fact, you could have written this in a slightly general way also, if you want. right? You can go ahead and write this in a general way where the number of conditions that you put on the variable is an input to the program. So the user will say that I want to go with the chain rule where the dependencies could be going up to 6, 7, k. Okay, so if you can do that, do that. Because if you do that, you may get some directions also for the term paper. Okay, because whatever I am discussing, the ideas behind those term papers are related. Okay, so that could be your initial lead into these things. Okay, so you can do that a bit, then in that case it will be interesting to see for L equals for 1, 2, 3, 4 how exactly the outputs behave, the generated quality of the generated data. And if it is really generic, then you may even go for black and white images, small one, right? Let's say 16 by 16 black and white images, and you can just linearize, make them into vector. And another thing to play is the ordering of this x1, x2, x3, because if it is a black and white image, right, so you need to do the ordering in the chain rule, x1, x2, like that. So the way we do is like this, right? So x1, x2, x3, then x4, x5, x6, x7. But which is a good ordering? Like should I go ordering like this? This is like this. Should I go ordering like this? So is it a good idea to do ordering like this? Because it will create different dependencies. So here the dependency of this guy is on this guy, on this guy, like this. Here the dependency on x1 is here, x2 is here, x3 here. So it looks into this guys. So which one is good, right? Can you extend this to a patch based method? Okay, I don't know. Okay, small patches. So many things could be done just in this framework. Okay, so the existing paper on this is Pixel CNN, Pixel RNN. They try to do on images, okay, color images, but that's it. This is more or less the idea. But then they want to build a neural network because as you see, as your dependencies are increasing, obviously your complexity is increasing, right? So can you build this into a prediction problem? Because if I have seen k pixels, can I predict the distribution when the dependency is on k pixel? Okay, it is a prediction. Okay, unlike this guy where I'm trying to do the maximum likelihood fit based on the sample, so you can say it is also a prediction. But if you use neural network, then it's kind of some nonlinear predictor that is acting like a like estimating the parameters of your model. Okay, so this is more or less the current thing going on. But initial intuition behind just this plain idea will help you a lot. So you may generalize this a little bit, but you will run out of computing time. As I said, this is an exponential. If you really increase dependencies each time, then we have seen that this is order of exponential. Okay, I guess 2 to the n something, if you recall. If you do the full chain rule, then I think it's exponential complexity, which is really not what we are looking for. Okay, exponential n going to just above 10, 20, and as I said, 10 to the 80 is the number of atoms in the universe. So that's why we fear exponentials. Okay, the moment the number of pixels in your image go beyond somewhere around 80 something, you need all the atoms in the universe. Okay, so this is the problem, and we know for sure images really go quite large. Even 32 by 32 is way greater than 680, right? So that's the problem. Okay, the difficulty of scaling, the so-called curse of dimensionality. Okay, so certainly full chain rule doesn't work for sure. Okay, as I said, you may try a very small grayscale image. As I said, very small one, let's say 8 by 8, 8 by 8 is already 64, so you cannot go for the, so what I'm saying is like you can try. So what I mean is don't go for the full chain rule, that's what I mean. Okay, it's not necessary that you need all, okay, because images usually have local depends on something local and then it keeps shifting. So maybe it's good enough that you have even for, let's say, 16 by 16 grayscale image, I may suggest that go for dependencies of 4 maybe, and still it will produce something interesting, I believe. Okay, I have not seen this, I have not coded this exactly, 4, 6 or whatever, so those could be tractable, because that will be still 2 to the 10 or up to 2 to the 10 something we can handle, I guess. Okay, and you may chat with me. There is a nice chat feature on this, but if you can give me some time in advance by email, then we can chat. Chat is more interactive, so we can take help of these online resources as well. Okay, so that was the assignment, and that will be quite important for the exam as well, especially the handwritten part. I will not ask the Python part, okay, in the exams. Okay. Now in the remaining lecture, we will focus on divergence measures, okay, and so divergence measures, the first one, the most important one is something called KL divergence. Okay, so K and L stands for those guys, Kullback and Solomon Kullback and Richard Liebler. Okay, so so these guys propose this in a statistics paper, actually in information theory and statistics paper, and what does it do? Okay, so it is known as relative entropy. It measures the difference between two probability distributions P and Q, and the original paper is cited here at the end of the slides, and it is defined like this. Okay, D sub KL, so D stands for divergence and KL says which type, because as you can see there are many types already, and P and Q are the probability distributions. So DKL, P and then this vertical bars is a very standard thing to say, and this mostly is for when you are comparing two probability distributions. So these are distributions, okay, that's the difference compared to other distance measures. These are distributions, okay, that's because in image generation and all, we are essentially dealing with distributions. Okay, so how can it be used? So basically we may say, okay, P corresponds to the actual distribution and Q is something I'm learning. Okay, so this could be used to kind of compare. Okay, we will see the details how KL is really used, but for the moment we want to understand what exactly it means. So this is sum over x. X sum is over the samples, obviously. So the possible outcomes, and you compute the probability values for those P of x, basically the PMF value if it's discrete, and log of Px over Qx. Okay, so this is a simple definition. P and Q are known to you, both P and Q are for the same samples here, so they take x in the argument, and it is Px log Px over Qx. That's it. That's easy to calculate. I have some examples for practice because this is so important that we will study this in slightly more detail. So where x denotes the elements in the sample space, KL divergence is non-negative. Okay, so this is the property. It says that it's always greater than or equal to 0. Okay, so it's non-negative, greater than or equal to 0, and it is asymmetric. So asymmetric means that if you do PQ or QP, they are not necessarily same. Okay, so this is not like the usual metric. If you define a metric or the usual distance, then they are symmetric. Distance of x from y is same as distance of y from x, but somehow it is not true for KL divergence. This is also interesting, that it is not asymmetric. So we cannot guarantee that this is a metric. We cannot say that it's a distance. Okay, the classical definition of distance requires that there is no ambiguity if I check distance from x to y or y to x. Okay, so that's interesting. So we cannot, that's why we call it divergence and not necessarily distance. Okay, because the concept of distance is quite general. I define distance norms between two functions and vectors, matrices, but somehow here we are a bit careful. We say divergence. Okay, so there are two main things we note. It's non-negative asymmetric, that is KL of PQ is not necessarily KL of QP. Despite these properties, KL divergence is widely used in various machine learning tasks. In fact, in generative modeling it is quite popular. Okay, now let us get a little bit of example in hand. So let us say the distribution P is defined by the probability values like this, and it corresponds to, I guess, binomial distribution with n equals to 2. So binomial with n equal to 2 essentially stands for 3 outcomes, because the third one will be the one that we didn't observe. Okay, so n equals to 2 stands for binomial, and the other one is a uniform distribution with outcomes 0, 1, 2, each with, so since it's uniform, as we know, uniform distribution, the probability values are all same for each outcome. So this is 1 over 3, 1 over 3, 1 over 3, and this is the binomial distribution we have, 0, 1, 2, right? So now KL divergence should measure the distance or like divergence, okay, between the distribution P and Q. Okay, so we have just plotted these values again just for our convenience. Like, this is how this distribution looks like, this is how this distribution looks like. Obviously they are not the same, so KL divergence should be giving us some positive value, not necessarily 0, because the distributions are different. So if we do the calculation, the maths and all, so KL of PQ according to the definition, yeah, I missed something here, I guess. P of Q, yeah, one second, this was this P guy, Px log Px Qx, right? Px log Px Qx, okay, although I have in the calculations, somehow I'm missing it here and here as well. Okay, so anyway, and here also we have to be a bit careful, I guess. There should be a typo here, because if I do QP, then Q will be on the top, so Q divided by P, and then Q here. Okay, so there is a typo here. I will try to correct this offline. And here Px natural logarithm Px Qx. Okay, so with this fix, then let us go ahead and calculate. So Px, first sample, because this is sum, right? So first sample, Px 9 over 25. So let us remember, okay, 9, 25, 12, 25, 4, 25. 9, 25, 12, 25, 4, 25. Those are the P values. Numerator also was Px, so 9, 25, 12, 25, 4, 25. And denominator was the uniform, so there is nothing much to do there. All were 1 over 3, 1 over 3, 1 over 3. That comes out to be 0.0852. Okay. And if we reverse, we do the QP, then with the correction that I mentioned, now here we have the Q values, so there will be 1 over 3, 1 over 3, 1 over 3, and Q are in the numerator, so there is an error here, right? So Q in the numerator means 1 over 3, 1 over 3, 1 over 3, and these are the P values, and this comes out to be 0.094. So obviously they differ. Okay, so PQ is not necessarily same as QP. You cannot also say that one is always greater or less, it depends. Okay, so this is the proof with an example that this is not symmetric. KL divergence is not symmetric. Now KL divergence may not be well defined, okay, but this you can figure out from the expression itself, right? When KL divergence is not defined, when it will go wrong, like when it is not well defined, when Q is 0, right? Exactly, right? So obviously we are not allowed to divide by something which is 0. So so this is problem, right? What does it say? It says that if there are samples, if there are possible outcomes that are never observed, that will create problem. right? But that can happen actually, right? It can happen many times. It may happen that I roll a die 10 times, I never observed a 1, right? So indeed KL Q, if it happens to be the roll of a die where 1 never appeared, for 1 it's going to be 0, and that will be a problem again. So that's, you may have to think what you could do in those cases, but yeah, so KL divergence, exactly that is created here in a smaller example, sample space AB. So possible outcomes AB, the P distribution gives you P of A is 1, P of B is 0, and Q distribution gives you half, so essentially uniform, and first one seems to be Bernoulli, and then we do KL of PQ, then you apply the formula, you get log 2, but this guy, if you do Q to P, KL of, then you get infinity, because at some point PB was 0. So here PB is 0, everything blows up to infinity. So you cannot really work with this when something is infinity. Yeah, so it's not really well defined. I mean, just the fact that I did not observe a B sample for the P, does it really mean that they are infinite apart? Okay, it's like if you use another measure, it's not infinite. Okay, that's the thing. So this happens with KL because of this issue that you face. So it may not be well defined, and one has to be a bit careful. Now in one of the things that we can do with KL divergence is we can generalize a bit slightly. Okay, so we can go from KL divergence to something called F divergence. Okay, so I guess I won't be able to go to the F divergence, but to go to F divergence we need some basic idea of convex function, because from KL divergence, if you see the KL divergence term, the way F divergence is a generalization of KL divergence is when I have, instead of log, I have F here, and this ratio is kind of reversed. Okay, and that's when we call it F divergence. So, and why would we do that? Because if we generalize the divergence with a generic F, so log here is just one possibility. That's what I'm saying. It's the negative of the log is a convex function. Okay, so log here is just one possibility. What if I could have taken some other convex function? This could have given me range of convex of measures, and some other could be useful as well. Okay, so that's our second our plan, that let us generalize. Why log, right? Why not? Is it possible that I replace log with something generic? And that something generic will be convex function. So some of you may not have done this convex analysis, so but the basic idea is very simple. So first thing is a convex set. So a set is called convex. If you draw a line between any two arbitrary point of the set, the whole line is in the set. Okay, so if every line between 2 points stays in the set, so line between two points x1 and x2 is denoted by theta x1 1 minus theta x2. It starts from x2 and goes to x1, and theta between 0 and 1. So this is the definition of a convex set. Okay, convex set, and there is also a concept of convex combination, where you can do theta I xi. In general, you take n points and you weight them by theta, and theta are such that the sum of these thetas are 1. Okay, that is important for convexity, and theta are also greater than or equal to 0. Okay, as a special case, you have theta 1 is theta and theta 2 is 1 minus theta. Both are greater than or equal to 0, and they lie between 0 and 1. But you can generalize and say it's convex combination. Okay, so this is convex set, and the reason why convex set is needed in convex function is because the domain should be convex of a convex function as well in the definition. Okay, so convex set is needed, and we can skip that. There are operations that preserve the convexity. Okay, so if I have a convex set, and if I apply a linear function on the convex set, then the image f of S will be still convex if S is a convex set. So these are these basic results. You just remember this. If I do an affine map, then of S, then that set is also convex. If I do inverse image of a convex set, that remains convex. Just remember this. Scaling of a convex set by scalar remains convex, because we can see this as a linear map that maps each entry to alpha times that. we can translate a convex set S, and if you just add each entry of the set S by A, still remains a convex set. Okay, so that's this basic results. Okay, now we come to the function. So convex function. Okay, so convex function is a function whose domain is a convex set. There are two things: set is convex, function is convex. So to define a function to be convex, first of all I need the domain of the function to be convex set, and now I go ahead and define what is convexity for a function. Okay, so f of theta x 1 minus theta y should be less than or equal theta f of x plus 1 minus theta f of y. Okay, so basically roughly what it means is that I draw the function graph, and I look at 2 points, arbitrary points x and y, then fx and fy, if I draw a line between them, then this is always above the function values. Okay, so that's a very so convex functions are again very simple. They are bowl shaped. Okay, they are always like this, they are always curving upward. So basically any arbitrary point I take x and y, these guys are always larger value than the corresponding these values. So that's what this inequality roughly means. So basically from here we can say that this guy is not convex, because if I take two arbitrary points, then the line joining them is below the function curve. Okay, so this is not convex. So basically convex functions are always like bowl shaped. Okay, always bowl shaped. And since there is equality, the linear functions are convex, because equality will capture all this. So it could be lines are convex, planes are convex. Okay, line joining them is equal to the function value. So these are convex. So this is about convex functions. Okay, so this is the picture, and we can define strictly convex. Strictly convex when it's strictly greater. Okay, and we can also define a concave function is concave if minus of f is convex. So basically a function is concave are always like this. So if I do minus of that, it necessarily reverses and becomes a ball shape. So this is concave, because if I do negative, then it becomes convex. So that's how concave functions are defined. As an exercise you can try. So how do you check a function is convex? So let us assume differentiability. Then one of the conditions is this: for all x and y, fy should be greater than or equal to fx plus grad f transpose y minus x. Okay, this is called first order condition for convexity. You can just memorize these results. If it is needed, you can use that later. So you are only supposed to just know the test for convexity. This is first order convexity, so use this as an exercise, right? E to the x is convex, right? So if you use the first order convexity, so how does it look like, right? You have to pick any x and y. Okay, x and y doesn't have, it has to be in the domain, that's all. But you can pick any x and y, and this inequality should hold. Okay, so what does this say? E to the y is greater than or equal to e to the x plus gradient. In our case this is a scalar function, so derivative, right? So derivative of e to the x is e to the x. So e to the x and y minus, oh sorry, why did I do, that's y minus x, sorry. So I thought fy minus, okay. So this is y minus x. So what we are supposed to show that e to the y minus e to the x is greater than or equal to e to the x y minus x. Okay, so for all x and y. Okay, it may take some time to figure out, I guess, but this is what we are supposed to prove. We can divide by e to the y minus x minus 1 is greater than or equal to y minus x. Is it true? It's true. How? Because y and x are any arbitrary, right? So is it true in general that e to the t minus 1 is greater than or equal to t. Is it true that e to the t is greater than or equal to 1 plus t? Why? So this is what you are supposed to prove. E to the t is greater than or equal to 1 plus t for all t. T could be negative also, because y minus x, right, arbitrary. So this is actually a known result. So you can prove that. So essentially you are boiled down to this. Try this, it might come in quiz as well. So e to the x first order convexity is true, is convex. Intuitively it is correct because it is like a ball shaped. E to the x function is like this, right? So it is curving upward. Same way you can prove that x square is convex. Use first order convexity. This will be slightly easier, straightforward, and this is slightly more because now you have two variable. Okay, so here you have x square plus y square, and now the gradient will be a vector. Okay, so what you are supposed to show now is fy, which is so here y is a vector now. Okay, so the second problem I can just formulate the inequality what we are supposed to prove. So second one is fy is like a whole vector. Okay, x y. So so let us say y is y1 y2 and x is x1 x2. Then what you are supposed to prove is that fy, which is y1 square plus y2 square, is greater than or equal to fx, which is x1 square plus x2 square, and gradient of f at x. So this is gradient of x1 square plus x2 square, which comes out to be 2x1 and 2x2. So this is 2x1 2x2. So this is a transpose, so that's why it became a row vector, and we have okay, y minus x. So usually vectors we see it as column vector. Okay, so here y minus x will be y1 minus x1, y1 minus x1 and y2 minus x2. Okay, this may be a little bit involved, like this is true. Is it true y1 square plus y2 square must be greater than or equal to x1 square? It may come out to be square term. Okay, if you bring everything together here, it may square it, like a square plus 2ab plus b square form. You write a plus b whole square or a minus b whole square. So you may bring everything this side, and it is likely that it will become x1 minus x2, I guess, plus y1 minus y2 whole square, something like that. Okay, so you may try that. So if it does, then this is also a candidate for convexity, and as you can remember, this is actually a paraboloid, right? So this is indeed indeed like this, so which means that this guy is curving upward, right? So this is a ball shape, right? So this is indeed a convex function. Okay, and this is first order convexity, but you know, many times you are given differentiable function, so it is actually easier if you go to the second order, because second order means that double derivative is positive definite. So let me go to the second order. Second order means that you take derivative 2 times, and if it happens that it is greater than or equal to 0, or if it take derivative 2 times, then it becomes Hessian, right? If f is a vector, if gradient of f is a vector, then if you take another gradient, because this is like 2 times gradient, right? So if you take another gradient, it becomes a matrix, right? So that's what you have to be a bit careful, because double derivative will make it a matrix, and in that case greater than or equal to 0 means that it's positive semi-definite. Okay, so positive semi-definite means that all the eigenvalues are greater than or equal to 0, but there is another check where we say that a matrix A is positive definite if x transpose is greater than or equal to 0 for all x. Okay, for all x not equal to 0. For 0 it is 0 anyway, for if x is 0, but so a matrix A is positive definite if for all x such that x transpose Ax is now x transpose Ax is a number, right? So then you can say its number is greater than 0, right? So x transpose Ax is greater than equal to 0. If it happens for all, then we say it's positive definite. So the second derivative test requires you to check that either the eigenvalues of the matrix great square f is greater than equal to 0, or this is the original definition of positive definiteness. You take any arbitrary x, and x transpose Ax should be greater than equal to 0. Okay, so with this I guess I can stop, and you can apply this on this problem. First two are easy, second derivative is just easy to calculate, but you can check second one. It is also easy. In the second one, it will be a diagonal matrix with 2 2 on the diagonal, which is a positive definite. Okay, so okay, that's all. Thank you.